But still, yeah, there's way more out there than meets the eye. And to get actually on topic tonight, wonderful. I'm seeing people coming to the chat. I'll put that away. I wanted to look at if by now, like you're realizing that there's an awful lot more than just infrastructure. There's awfully, if you've done the Python course as well with Charlie and the like, you can implement some form of business logic or some application design on a server using something like a programming language. And even if you want, we're able to generate web pages with that too. So we've seen then on the browser side, the so-called client side, how you're able to render information up on the screen for us as end users. And so with CSS, you may be able to style it. With JavaScript, you can make it more interactive. But when you're building any business or any application with end users, my question is, where is the data actually going to be stored? And so that's what I'm going to talk about tonight. I'm going to, before I forget, I'm going to send over a quick sheet that I had prepared for this. If I find it, that'll be useful. It would be great if I had it to hand, but of course, everything is closed. And so I will send that over now. Perfect. That's just a little bit of a handout should you want it, okay? But that's what I'm reading from. When you are working with databases, so if you're running your own business, okay, maybe you might simply be using a simple spreadsheet. And of course, spreadsheets, the way we know spreadsheets, whether they're implemented in something like Microsoft Excel or Google Spreadsheets or Apple Numbers, generally those things store information in rows, left and right rows and columns up and down. And so if you're like me, you probably use that first row in a spreadsheet in order to have the names of the columns and the types of data that appear in that you're storing. And then you start to continue adding more and more and more data into that spreadsheet, probably like me eventually, you continue to add row after row after row after row. Meanwhile, if you've got so much data and so many different types of data they're in, and data that doesn't really belong into just one sheet, you might then actually go ahead and create yourself a second sheet, or a second tab perhaps along the bottom of the screen, for instance, in which you can then add in and store additional data in there as well. So indeed, like Microsoft Excel allows you to do that. Microsoft Excel allows you to store data relationally, so to speak, where you might have, say, example, you might have one sheet with customer information and another sheet over there with, say, invoice information, if you like, business or something. Another sheet over there would say your products or your services, other types of data. And the idea is that you're then able to somehow or other relate those by thinking about some commonality between your different types of your different sheets. Yeah, some identifier, perhaps some name or some customer ID or the like. And so that data tends to be again stored in rows and columns, and these then are able to contain relationships between them. And certainly we can do this in the cloud nowadays as well as with Google Docs and the like. Simply having a web-based version of the same. But when you're designing your spreadsheets, or more generally, when you're designing your schema, the design thereof, there is a number of questions that you have to consider. So what do you want to store, first and foremost? Where do you want to store it? What even type of data is it to begin with? Because whether it's using Excel or Google Sheets or anything else, odds are that you sometimes configure the columns to be displayed and to be formatted in particular ways. So numbers, for example, might be displayed without commas. Numbers might be displayed with or without pound signs or some other symbol. You might want to separate one field from another field using some special symbols or some punctuation or the like. So these are all configuration options with a spreadsheet that might be amongst those first decisions that you end up doing. And so if we have a look at the kind of sample spreadsheet wherein I would like to work on. So if we consider a sample spreadsheet, if we think about going to Google Docs, for example, here, and if I'm a company and I want to represent users of my company in some kind of a web application, for example, all of us have, of course, at this point, we've all registered for a website, we know what it's like, we've all gone for an application. And so the kind of questions you tend to be asked by a website or an application are things along the lines of, say, your username, for example. Often you're asked who do you want to belong to. You might be actually asked for your actual name then, for example. What else might you be asked for? Or perhaps how to contact you, something like your email address. And perhaps if you're buying something, if it's like a store, perhaps, if you're registering to buy something or someone needs to know a bit more about you, perhaps they'll even ask for things like your address or perhaps your phone number, maybe as well your age too. So you can suddenly imagine there being other kinds of fields that you might need for this. But then consider what types of data each of those fields is. So what should a username be? Well, by definition, I tried it today. Actually, I tried to make a new email address and I couldn't. I was fighting with it for a while because it had been taken. Someone else had parked in that spot. Usernames usually are unique, something that is going to be belonging to you and you alone, or at least in that system, there's only one of you. So for instance, if I'm registering for a website and that website is storing some data in that website, for instance, like a spreadsheet, then I might ideally try to claim something like Markoverse as mine if it's available, okay? And so, for example, if my name, for example, that'll just, of course, be my name. Let's just say that, Marco Paul. Someone else can have that name. It actually exists. Someone else does. Hopefully, though, my email address is only mine. So I'll say marco@cloud.com. And of course, that will be stored in a column of its own. Then my address, for instance, like for here, I'm going to say my residence of 42 Wallaby Way, Sydney. All right. If let me push that out. For my phone number, then, let's say I can be contacted on 0800 00 1066. That stayed with me for life. And by age, I'll just leave that blank for now. So notice then how all of these pieces of data, all this data is a little bit different to one another. I mean, just by looking at it, you can tell roughly. For sure, some of them seem to be numeric in nature. Some of them seem to be more alphabetic in nature. And some of them even have punctuation marks within. Now, you might or you might not, in a spreadsheet, care to display this data a bit differently. Again, the only number I'm really sweeping under the rug here is, say, my age, but hopefully I don't need one or more comments in that value, so that should be fine. There isn't any need for special formatting for that one. But it turns out that when you're actually building a website, when you're building some software-based application, You're probably not just storing your data willy-nilly in ultimately in spreadsheets. Hopefully not. You might eventually graduate from being a small shop or a small business into needing something more than just Microsoft Excel or Google Spreadsheet, for example, or something cloud-based like this. Why might that be? Well, again, if you and your company has maybe more rows to display, more rows that those programs generally can handle. In fact, on your computer, on your Mac, on your phone, odds are that when you're opening really big files up, if you notice opening a spreadsheet perhaps or some other documents, sometimes you might feel that struggle. You'll actually struggle with the computer, right? If you start to open up something enormous, your computer might start to slow. And you might see that the spinning beach ball if you're on Mac, or the hourglass as well, because what you're doing is you're hitting the limits of what your local computer, what your local device can actually do with its client-side software, like a spreadsheet tool. It's only finite. And so eventually, you might actually need to think about using a proper database and upgrade from something like this. And the database really is just a special, it's software. Database is something that can absolutely run on your computer, on your Mac, on your PC just fine. But very commonly, databases tend to not run on our computers, but run on something like a server. Database server, ideally somewhere else in the cloud, which to which your computer then connects to. So, for instance, if you're building a website or an app or something in a language, say like Python, for example, with Python, you can write code that talks to or communicates with that database, and you're able to pull data down and send data back up to that database from your machine. But still, in this world, spreadsheets are really straightforward and wonderful for that regard. It's just so intuitive how I got here. I mean, just typing Google Spreadsheets. It's really intuitive how you then store the data in rows and columns, and there's just much more than rows and columns than as you start to think about more and more data. So what's nice about some databases is, I guess, databases are trying to mimic this design. So what other possibilities might we have when it comes to this? When there exists in the world of relational databases, of course, what we said, the most common ways to store data is still today, to this day, relationally. And the jargon is a bit different in the world of databases because, for one, we're no longer going to call these things spreadsheets. We're going to call them databases. We don't call the individual tabs sheets, okay? We call them tables. But we still continue to structure the data. We start to think about the rows, the data they're in terms of rows and columns and additional pieces of data for columns and rows, which are for the different types of data they're in. But in a relational model, so such as Oracle and Microsoft Access and SQL, MySQL, MariaDB, Postgres, and so on, something smaller and lightweight actually called SQLite, which I'll show you later. The burden ultimately is going to be on you. The designer of the database, the programmer perhaps, the business person to whom actually decides on what type of data you're ultimately going to be storing in. Because the database, in order for the database to be able to handle more and more data than the typical spreadsheet would typically supports, a database is going to need a little bit more information from you. It's going to need some help from us. It needs to know what type of data you're going to be storing in the database so that it's able then to categorize and search within and handle it more efficiently and sort of sort it more effectively and ultimately make it much more easier for you ultimately to add and remove data from that particular database. So in other words, you can do all the same operations that we've just seen with a spreadsheet, but generally in a database, you have so much more data you're going to need to have to help the database help you back. The more you put in, the more you get out. All right, so what does that actually mean? We need to consider a couple of fields then for that. Okay, we need to think about how to help it. If we want to migrate my spreadsheet with many rows of users, let's imagine, for instance, to a proper database, a relational database in that case, we're going to have to make a couple of more decisions with that. And as it turns out, it's actually a good idea to start with the types of data for those columns. I'll say this for now. Generally speaking, in a database, MySQL, SQL Access, and the like, you only have a limited amount of options, really. Some of these are defined, okay? So you take a look at some of these and realize what they might be. So on screen, you can see a couple, and many in the relational database world, again, these are just some, there's more that are available to us, but here's some of the most important ones. Take, for example, the integer. So the integer is what you think it is exactly. It's just a full number. It's something that you need to represent like a 1 or a 42 or a negative 273. A real number, otherwise also known as a floating point value. For instance, again in Python, if you know a float, that is actually something with a decimal point. Okay, so perhaps some numbers thereafter. We've got numerics, which are kind of a catch-all term that might handle things like currency and dates and times and other numbers in that sense, but you still have more formal structure to them. We'll see that in a second. And then more generally, well, moving on from integer values into more like alphanumeric values, so general text, that's what it's called. Text is where you have more like words and more like phrases, characters, or even full paragraphs, or more that you might want to store as well in some form of column. And lastly, we also have the cutely named blob, or a binary large object. Microsoft Azure actually just call it blob storage. I think that's cool, where you actually just want to store zeros and ones and zeros. That is to say, your binary data, like actual files in your database, if you want to store them like that. However, you don't really need to do this typically, and it's a design pattern that we frown upon. I mean, you can actually store files, of course. You can store files on a file system and your own hard drive somewhere on the server, but that option is also possible. There are design decisions around that too. And I mean, this is a non-exhaustive list. Like, it happens to be the list of data types supported by pretty much all of them, the simplest of relational databases, namely something that we're going to see called SQLite, SQLite. Good evening, Anko, just so we have a message. So with SQLite, pronounced, well, I think SQLite, it's as the name implies, it's a lightweight version of SQL, and it actually supports a very specific language which anyone can request data to and from the database and store data into the database or update the database or delete it from the database. And that language is, of course, the structured query language, or SQL. And SQL is a language by which you're probably familiar by now, but it's one that you can do exactly this. You're able to retrieve data from the database, it's able to put data into the database, and a whole lot more. So this is SQL is more of a programmatic alternative to pointing and clicking, with which you're probably familiar with something like spreadsheets or the like, where it really is just you, the human, doing all the work via a graphical user interface, a GUI. Now, to be fair, in all these spreadsheet programs, there are functions, there are macros that you might be able to write. And in fact, I just saw that when we first opened up. It did pop up and give me a couple of options for that in terms of macros, so that I might be able to write them in these environments like this, for example. But still within some limitations. There you go. So that's exactly what I'm talking about. There is something, some functions therein that might be able to emulate this idea. And indeed with SQL and with SQL databases more generally, that is databases that understand this language of SQL, you're able to achieve high performance. Can you store far more data in a relational way and nonetheless get at it faster? Okay, so a relational database is sort of the next evolution of what you might otherwise do only within your own spreadsheet, only within your own computer. But there are many other databases. If you look at the relational database service, engine-wise, you have, this is just to name but a few. Microsoft SQL Server, MySQL, Oracle, Microsoft Access, Databricks, Snowflake, FileMaker, and the list goes on. Okay, support that. A lot of these actually support those data types we just looked at, and will help you help the database more because you help it and it'll help you back. Because the idea is that the more that we help the database, the more considerations we make towards it, the more the database knows about our data, let's say, the smarter the decisions can it make at a lower level, at a more programmatic sense, below those abstractions that we might otherwise get, say, using a spreadsheet. Because a database is then able to store that data, so when you have a question, you can answer it much, much more quickly. Cool transition. All right, so how let's take a look at this. We could refine then what we think of as an integer then. So in some databases, you might want to tell it that it is, just a small integer in one column, and maybe one after another, row by row, or maybe it's just an integer somewhere a little bit bigger than that one, or perhaps just a big int, perhaps, it means that it can be larger. Now, these actually map to very well-defined values. If you think back to, think about how we consider data itself to be stored in a computer, if you've been in those sessions before with me, ultimately, data is always going to be just stored in ones and zeros on a machine. And indeed, an integer, so to speak, or an int, generally takes up 32 bits, okay, or 4 bytes, let's say, because 1 byte is 8 bits. But of course, that few bits is actually, it translates, if you do the math, to 2 to the power of 32. That's that nice round number we come across a lot in networking, or 4.3 billion, roughly, give or take, possible values. And so, if you're able to specify that a column in your database is of type integer, if you say that to the database, if you tell it in advance, that means that you could store, you could type in the number, anything from 0 all the way up to 4.3 billion, or if you want negative numbers from negative 0 all the way to minus that as well. But beyond that, beyond 3 or 4, you're actually out of luck if you're just relying on 32 bits alone. Now, it might seem huge if it was, I can't remember counting that high, and indeed, it's a good problem to have, I suppose, if you have 4.3 billion sales, or 4.3 billion users, or 4.3 billion anything in your database. Like, that's a lot of customers, let's say. That's a good problem in that sense. But again, for certain larger companies or some specific telemetry, actually having 4 billion records, let's be precise, of some sort, some transactions, some logs, it's actually not that uncommon either. Okay, so it can happen. And again, for those purposes, then, when you're thinking about having more than 4.3 billion, there does exist then the big integer in that case. And that's just a bigger type that uses actually 64 bits or 64, or basically 8 bytes, okay, with which you can count then many, much higher, so high that I don't even know. Let's get the calculator and figure that out, 2 to the power of 64, and exactly that many, 18 quadrillion or something, whatever. I don't have to pronounce it, but that should probably be enough for all of our purposes, needless to say. So ultimately, it's not enough then just to say that the field in the database is an integer, but actually, maximally, what's the ceiling? How big can that integer really be? Now, fortunately for us, I think, back to my spreadsheet, I think age we can probably get away with a small int, but again, with like a small int, you typically have 16 bits, because 2 to the power of 16, 2 to the power of 16, yeah, 2 to the power of 8, or 15. Well, it could be exactly this. Like, if it's that much, I see, yes, because from negative up to positive. So all in all, that makes sense. Yeah, 64,000. So again, if your age is underneath 65,000 or so, I think you'd be fine getting away with this. Otherwise, think about something bigger, okay? But there's more. What then? I always found this funny. What about real numbers? These real numbers are floating point values with decimal points. And so here too, you tend to have fewer choices typically. But again, still along those same lines, a real number would typically take up 32 bits. Okay, so 4 bytes of storage, we know that 1 byte is made up of 8 bits. And so if it's 4 bytes, we end up with 32 bits, which again allows you only some amount of precision, up to 65,000 characters or so, some number of digits after that decimal points. Okay, so whatever it is, 1 point, up to 32 further down. So, sorry, up to 65,000 further down, which up to a point is great. But if you want to get even further, if you're the kind of person that needs to be that precise, you can then actually occupy twice the amount of space, literally 64 bits, or 8 bytes in that case, use double precision instead. So it would seem then that we sort of start with an okay value and with an even better value there, and that's it. But ultimately, like, what is the trade-off between these two, as there always is? Well, it's fine if you want to be able to count higher, whether that's with integers or with real numbers, but if you are counting higher and higher and higher and getting more and more precise, you're literally going to pay a price, aren't you? Because again, if I want to count higher than 65,000, or if I want to count higher than 4.3 billion in the context of integers or reals here, well, you're going to literally occupy twice as much space because you're now occupying from 4 bytes all the way to 8 bytes in order to store those values using this data type. And again, if you're never actually going to use values larger than 4 billion, then you're going to be spending twice as much space than you actually need it to. So is that a reasonable thing to do? Again, for smaller databases, that might be inconsequential. You probably won't notice, but again, that's for the Googles and Microsofts and others of the world to deal with in terms of gigabytes and terabytes of data. Because all those bits and all those bytes will eventually, surely, all add up. So what are the types? Oh, and just for those that joined a little bit late, if you can't re-watch or can't read back in the Zoom chat, I'll just send over the spreadsheets again, just so you have a copy of the handouts. Just for those that didn't get that earlier. So there you go. Perfect. So we're looking at types of data, and as for, in our case, numeric now, numeric is kind of a catch-all in that case, numerically, so to speak, because you're able to, whereby you might have things like booleans, which are ones and zeros, or true or false, is or isn't. You also end up with dates, which is much more in a, this comes in a more prescribed format for you, typically year, dash, month, or month, date, or something along the lines of that. Even though, like, across the world, there are different formats in different communities, we represent different times in different ways, okay? But at least in SQL, you have to define them in exactly that format. Like, there's only one way of doing this. Date time actually allows you to add a space to this, followed by hour. So you've got date time, which is hour, minute, second after the date as well. So if you want to store both the date and the time together, you would store that exactly in this kind of format in your database, even though, again, thanks to code, whether that's Python or SQL itself, if you want to display that date in a geographically localized and more conventional way, you nonetheless store that in that way in your database. Now, sometimes you need to fight against that imprecision, thanks to the real inherent risk that is with real numbers. And so you can use this kind of numeric data type as well, just to specify a so-called scale and so-called precision. That is, after choosing numeric, you then have to say 2 numbers to then specify or define really how many digits thereafter you ultimately want to support. So if you want to think of currency, think of pounds, like how many pennies or how many hundreds of pennies, 4 or 10 or how many decimal places thereafter, can you specify exactly that, okay? You will get exactly that much precision. As for timestamp, so that's really just simply, so hour, minute, second, but timestamp's a little bit more interesting because it can also be used to say, like, it can really represent time, but as well with many languages, Python and JavaScript amongst them, there's 2 typically resemble by counting some number of milliseconds or seconds from a particular point in time, so from here to there. In fact, some time ago, quite interestingly, if you look at it, the timestamp originally started. So when timestamp was originally made, again, so that's the format that we kind of get, and it was remembering sort of counting of milliseconds, counting of seconds from a particular point in time. It was conventional actually to use it from a single, it's always 1970. So I guess on some day we all decided, let's start counting time from the 1st of January from 1970, so to speak, the so-called epoch, which is what they said, as opposed to say like 0 BC or AD or the like. Okay, so that was like, SQL considers that's the dawn of civilization. Unfortunately, it turns out that you generally support these timestamps with 4 bytes or 32 bits, which gives you access to 2 to the power 32. That's 4 billion or so answers. And so that means that ultimately, if I think it's the year, when will we run out of digits or bits to represent time? Sometime in the future, we're going to have a problem. What on earth is this? Not interested. There you go. So there is actually a problem in the not so far future. If you remember the so-called the Y2K disaster, where we ran into this problem in the year 2000 or so, where we sort of painted ourselves in the corner of many systems by not having allocated enough space with an 8-bit system to get us past the year 2000. Well, it's going to happen again, folks, with a 32-bit system in 2038. I guess what's the solution invariably going to be? I guess inevitably use more bits, right? Use more space and thus more cost, I guess. But that is inherent in just so many systems. So that's one of the things that we humans will have to address and we're slowly pushing towards and getting into. Okay, so what else? So how about text? So text as well can come in all kind of multiple forms, whether that's in English or some other languages as well, and you're going to have multiple lengths thereof. And so within the world of text, values, and databases too, need to specify typically how many characters you want to store in that column. And this is distinct, different from something like a spreadsheet program where you probably keep trying and pasting as many characters as you like to, whereas a database, insofar as the purpose in life is to give you better performance and more scalability than a spreadsheet would allow, wants you to tell it a bit more. The database is going to ask you to decide in advance whether you want to store a fixed number of chars, of characters. So character, typically followed then by number, small n, represented here as like n means how many characters exactly shall you store in every cell in this column? How many characters are going to be occupying that? What might be applicable? So, for example, well, in Brazil, okay, for instance, for states in Brazil, we have a standardization in Brazil of 2 characters for every state in the country. So I might then say something like car 2, for example, thereby allowing you to Rio de Janeiro, you might have SP for Sao Paulo, you might have ES for Espírito Santo, and so on, because you know that every value is going to be that finite length. It's going to be 2 characters in length. But sometimes you don't know the max length. This is one of those privileged examples where we do and we have the foresight, but what if we don't? What in the case of, say, my users, for example, in my own table of users, for example, my own name, for example, I'm not making this up, I was cursed, M, 2, 3, 4, 5, a space, 6, 7. Well, I'll just type it. I can't think and type. Alejandro, Ball hyphen A. It's so long it's on our screen. So it's basically, I can, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 26, that's one I hear. But basically, I have a very long name, okay? Your name probably will be shorter or might be longer. But of course, some user that hasn't even registered for our website yet might have an upper bound or a longer name than even that. So for that reason, we have varchar, or variable character lengths. So that exists too, where you can specify a not a fixed length, so not a ceiling or a fixed number of characters to use, but rather a maximum upper bound, as much as to this point. Perhaps something like 30 or 40, or more realistically like 100 or 200, or something. Some of the characters that you decide that's going to be the upper limit that any human that I actually see in my sites with any realism would probably have a name as long as this, as many as this characters, let's say. So that is varchar. Varchar is pretty smart, and the database that will use varchar will know how to use it because it will use that many characters maximally to say like, oh, it's going to use up to 30 characters, but it's not going to waste space. So in fact, if I'm using 30 characters, and for every name in my table, for example, well, it's only going to store as many characters as necessary, plus perhaps a little bit of overhead for accounting just to keep track of value. But that way, you actually do save space, but you still can handle large text or large strings. Lastly, if you have a really a particularly large text, whole paragraphs, essays, if you will, just documents that someone might paste in, the contents of a whole web page, for example, something that you might want to search. Well, for that thing, you have a text field. And, well, you can have a text field more generally, which tends to support tens or thousands of more characters in general. So, but it does so in a way that's just not as efficient. So rather than trying to keep it tied to the column itself, so to speak, it actually puts it somewhere else on the server. The result of it, which is that you can then you can fit more room over here, so to speak, but it will take more time and it will take more effort to go on and search and find that data within. Again, always a trade-off between space and time. That's the trade-off. But here too, as we saw with integers and as we saw with real as well, you seem to end up with multiple choices. One of which is, at a first glance, is better. After all, why would we ever use car if we could also just use varchar as well with that same amount? For instance, those two character codes we just talked about for states. Why not just use varchar2 and not just car2? Sorry, Ben, wrong way around. So why would anyone go for this instead of that? This rather instead of this? Well, as it turns out, that if you promise the database that for every cell in your column will be exactly the same number of bytes, it turns out that you actually have a very straight or justified edges in some sense conceptually of that column. For example, if every cell in my column takes up exactly the same amount, it will always be the same amount of space, then you might know if you start numbering the bytes, the bits, that are represented by those cells. So this might be 0 bytes there, and then this might be 2 characters down the line. This will address 2, and then 4, and then 6, and then 8. And then if you think back to my section on how algorithms work, say something like binary search, think about how binary search is implemented. Soon enough, then you have the ability to know algorithmically where the next value, or the last value behind it, or better yet, the kind of the middle value is, numerically, you can just jump right to it in so-called constant time, thereby enabling you to something like binary search and ultimately logarithmic time. So this is a really powerful thing, okay? If you commit to the database ahead of time, if you are fixed in your schema that all your values will take up this exact amount of space, the database, knowing this information, can search for that data faster for you. varchar, ultimately, unfortunately, it's a bit like on a document where you end up writing and somehow you have a left justified column whereby you sort of have some lines of text which look very straight on one edge, and then all the characters are left aligned. They're all straight on this side, but all the length of those characters may vary. So this might be this wide, that might be that wide, this might be that wide, this might be that wide. So they all change ultimately. And so because you have this very ragged edge, in that sense, you just can't do simple maths on this. You can't just add 2 and add 2 and add 2 to get to the next value in that column. So in the worst case, like if a column is only varchar, then the best the database can do is just a linear search or big OFN, and which remember was it's a lot slower, noticeably slower than something that's like log n or logarithmic time. So point being that the more help you can provide the database, the better you are. But of course, you don't want to err too much on the other side and just say, well, I'm going to have car 300 for my names column, because if you're using 300 characters for that definition of names, and my name was 26 characters, who just needs a few, it's going to waste an awful lot as well. Okay, and this last one as well. So this thing here, blob, the binary large object, which can just store binary data. And that can be used then for files, for images, for the like. But then again, these things, like S3, it tends to be stored somewhere else in that system, okay? Okay, so let's have a look at our system. So then, if we have our data, okay, let me go back to my spreadsheet. Again, with these possibilities in mind then, how might we go about by designing a schema for this table? For all my data, this is the kind of thing I'm going to store. So we already have the names of the columns. That's what I'm defining here. That's the name of my column. And I've already gone ahead and I've put one sample row in my database. So let's consider then in the context of all the SQL types that we just discussed, like which ones are going to apply here? What best fits? Well, let's start with username. For username, something like Markoverse, well, it's definitely not something numeric because it's not something I'll be inclined to type. It probably is text somehow. But within text, remember, we have a few choices. We have a choice of car, we have a choice of varchar, or larger blocks of text as well more generally. So which one should it be? Actually, this one is a tricky one. It actually depends. So a user tends to be fairly short because after all, like we humans don't want to type in very long strings just to log into some site. So historically, maximum values of 8 characters was really common, but that trend seems to be fairly constrained, and you can no longer express very well your name if you tend to have a long name yourself. So here we might say something like, let's say car, because we know it's going to be small and we would like to be able to search for it on this field efficiently, so to speak, especially to log someone in fast, but it's probably not going to be quite as short as 8. So maybe let's say 16 or actually 20 characters as well. Or if it's hard to guess there, if you want more dynamism, if you will, let's say maybe perhaps varchar 255. Why that value? Why variable character? Well, remember, if I pull up my calculator with 8 bits that's stored here, so 2 to the power of 80, 2 to the power of 8 is 256. All right, but again, remember, if you're counting from zero, you can only go as high as 255. So historically, many databases will have a limit of say 255 for a varchar. That's not exactly longer the case, but you still commonly see that nowadays. So what's the best answer? I don't know. I can tell you. It depends on your data. It depends on someone else's data. For here, I'm just going to leave it ahead with varchar. I'm not going to touch it, just to give myself a bit of flexibility. But a good argument could be made for car as well as some smaller value, or even varchar of some smaller value as well. As for name, this column, well, I'm not really sure what this one should be either. Like, I don't know how many characters your own name has. Mine has quite a lot. Something like 9, for example, is probably too few, even though it satisfies my name just fine. 30 feels a little bit tight. And frankly, I bet if I Google the longest name in the world, longest name in the world, something tells me that someone out there, this guy Hubert, wow, by quite a few characters. What? Oh, okay, he's one of those guys who just takes on every name. So he would definitely break this if I were to say no more than 255. But hopefully, aside from Hubert, who I don't want to let in, that should be enough. I should probably do some due diligence, okay? So I'll say the same. With email as well, that seems to be easy. Again, this is just characters, even though you can certainly have numbers as well. I don't know how long the maximum email address would be. I don't care to look, but frankly, it's probably going to be something variable as well in length. So I'm just going to stick it in with the default of 255 again. Why 255? Again, it's probably more than we ever need. I'm sort of stretching out, but varchar is clever. It's smart in that sense. Varchar is not going to waste it's not going to waste that many bytes. So what you'll do is you'll just set a reasonable upper bound on the in the absence of a better intuition. As long as we're being consistent, that's fine. Now on to something else. What about address? Address will be decently long for sure, especially if if it's going on an envelope, say multiple lanes. But here is probably just going to be some text. And so what I'm going to say is again, varchar 255. Now phone, finally, a number by name. So 0800 1066. So what should a phone number be? What should that field have? Well, we had integer or real, or more specifically a small int or an int or like a big int. But the funny thing is here is that even though a phone number is actually, we humans think of it as being a number, it's actually not. It's actually just a symbolic representation of a unique identifier for someone's phone. And so it's not uncommon to see hyphens, in one culture, in one community. So you could have, I've seen like in Brazil, we'll have something like a parenthesis, plus some country code as well within. So frankly, like, does a phone number not become a number so much, but actually a textual string again? And so again, here we have a bit of discretion. At least here now, I could be presumptuous and say, I'm going to assume that I'm only going to have customers from, or let's say users from maybe just now the UK, or whatever business constraints I might do, and say, well, you know what? So this is a candidate to say, I might do something then like car, but 10, okay? Because that means it's a 4-digit area code followed by a 2-digit exchange followed then by the 4 digits thereafter. Now, it doesn't really leave you much room for those spaces you see between this and that, that space and this space. So perhaps, an argument to be made, I could make it 12 to account for those as well. Or frankly, like, if they're going to be there all the time, then why don't I just leave it as car 10 and just get rid of those altogether in there with my data? That's also a solution too. Alternatively, I could support spaces, I could support parentheses or pluses as well if I want to. It really just depends ultimately on how you want to store your data. But I like this idea. See, something funny happened there when I clicked off it. I like the idea of a textual type, something like car or maybe varchar as well, as opposed to an integer, because at least if I'm called, certain communities or some other businesses, sometimes you end up with unusual numbers. And in some countries, for instance, here, if we generalize beyond just this data set, like in the UK, do we have 0 at the beginning of our number to actually connect to someone local? So 0800 numbers, for example. But the problem with 0 is exactly what you just saw on screen. Like mathematically, 0 is meaningless to start a value with 0. Okay, 1 is the same as 0, 1. And unfortunately, a computer takes that to heart. And so if you were to start a phone number as an integer like I just did, but again, if your phone number started with a 0, like mine does, then my database just gets rid of it because it says I'm not going to occupy space. So that you just want me to do it there. I'm going to say 1 or 0, 1, and it just goes away. Depending again on how you format the column, you can type in as many zeros as you want, and then followed by a few other digits, and when you hit enter, those zeros are now gone. As for age now, I'm just going to have, well, let's have a compelling candidate now for a number. I think small int will do just fine. Integer would work as well, but, or big ints, but again, increasingly wasteful. But you know what? Even though it's not that obvious, I should probably not use the integer type here at all. Why? Because, so when you log into a website, when you ask a human for his or her age upon registering, the catch is that might change, the next day, or that might change the day after, because, of course, time is advancing. And unless I also store the date and ideally the time at which the user registered, I can't really even do any math and figure out, okay, well, you registered a year ago. Let me assume that your age is that year plus 1. So what would actually be a better age from the get-go than age? It's probably something like DOB. So for date of birth, that's also 1. And of course, in SQL, we do have the ability to do this. It's just dates, okay? Date plus even maybe times. So here we probably have a better candidate for one of those in your numeric data types, so to speak. Now, all in all, we've only just begun to scratch the surface of all those available data types that we've of course got to hand. And there's many more out there still. In fact, our spreadsheet or our database can have many more, as you can see, many more types of data. But now let's just assume that we're happy with the current data we've got. We're fine with the ones we have. And the goal now at hand is for us to start searching our data. We want to be able to store that data in an actual database. Because up until now, I've just been using Google Spreadsheets, just to sort of lay out the schema sort of visually as a worksheet, if you will. But now let's graduate over to an actual SQL syntax. I want to see some syntax and suppose that this same data is now stored on Google Spreadsheets or something else, but actually in some database elsewhere. So I want to store this in some piece of software running somewhere local, maybe some other computer or perhaps somewhere in the cloud that knows how to organize this data. Still in rows, still in columns, but in such a way that I can use this new language that we talked about, this SQL language, in order for us to go ahead and access my data. I guess these are the ones that we should probably look at the most. I mean, the fundamental operations that SQL supports, or a relational database, more generally. It turns out that throughout computer science, there has been a pattern of operations that many different systems today support. In the world of relational databases, you might have, rather crassly, what's known as CRUD, the ability to create data, or to read data, or to update data, and to delete data too. And more specifically, again, in the context of SQL, this new language, at last, you have to somehow think about creating the data, or selecting the data also, to be able to update the data, aka insert data, as well to update and delete the data, okay, drop data as well. So whereas in SQL you have these very specific terms, these are just otherwise representative of a class of operations that you might otherwise see throughout computer science. Okay, so how do we go about by using this? How do we get SQL? Well, short of just buying something and installing something like Oracle or downloading something like MySQL, we can simply use something that's, indeed by definition, lighter weight, called SQLite. SQLite is what we'll be using. And SQLite is an implementation of SQL, this database language, which, again, you can install it on your own Mac, on your PC, and it uses not a special software or special service, but really just a file on your computer, just a file on your PC that stores all those tables and, in turn, all those rows and columns. It thereafter creates an abstraction of sorts, and as though you would have a full-fledged server running on your own machine, with which you can then communicate via SQL. In fact, let's have a look. So if I, so right. In fact, one of the easiest programs to use is this one right here. So DB Browser is called. So DB Browser, as it's now realizing very zoomed out and I can't zoom in, but DB Browser, freely available for Mac, for PC, running on Windows or Linux, DB Browser, or any number of other operating systems as well, is this. In advance, what I've done is I've gone ahead and I've set this up. So I've opened up a file here in the database whose name ends with a .SQLite, okay, or more commonly as well, .db. Which then, again, remember, this is just a file. It does have a I was thinking exactly the same thing. It's so funny, I was thinking just that. Does it have one? Shy of just taking a step back on my computer, I don't think there's much I can do. Remember, this is not a full, many preferences. This looks promising. Let me Google it. Does DB Browser have dark mode? Where? How? No. Preferences, settings, find the general appearance. I think that might just be the hallucination though, because it was just a general appearance. There you go. Wonderful, nice one. So this, to be clear, is not a database. It is just a file. The file is called Chinook_SQLite, which is like a common data set that exists out there. You can find it online. But it is just a binary file that I've made it read, filled up with ones and zeros that collectively form then the pattern of rows and the pattern of columns, and the tables that contain that then within. And so if I open up this program, I see the list of tables. I see, if you will, the sheets from our old spreadsheet world. So this then happens to be a database all about music. And again, if I have a table all about music, musical artists, musical albums, musical customers and employees and genres and invoice lines and so on and so forth. Things that actually represent strong sports, the types of media, the playlists, or the playlist tracks file, then users can actually synchronize or customize their songs with. And lastly, the tracks of the songs themselves. And in other words, someone on the internet has actually gone to the trouble of aggregating all this data that exists about music and all the authors and organize that into a SQL database. Now, how? Well, if you look at the table right here, again, and you'll see a lot of these esoteric commands to the no. Closing that for a second. How do I get back? Oh, goodness me. What? I don't have to get back. Let me close it and open it again. SQLite database right there. Okay, no, it's still insisting on having the schema shown to me. So, DB Browser. Okay. I think I might have clicked on something and then hidden it from you. Where is it? It's there, right? Oh, no. Well, it doesn't really matter. Okay. So because I want to have indices. For the sake of these commands, I mean, the ones that are off to the right here, they involve things like creating table. If I hover over, actually, it tells me more. Indeed, the word create is one of those four fundamental operations of create, read, update, and delete of CRUD that SQL supports. And without going into too much of the weeds about how these tables were even created, they were created in such a way that the author had to then decide on every table's columns and every table names as well as their types. And that part is interesting. So for instance, if we go into the albums table here, and if I expand this one now, I find inside of which album ID and title, and curiously, I also have artist ID. But notice that in the album column, we have no mention of the artist's name. In fact, if we follow the rabbit hole here, if I then open up artist table, okay, that's in the artist table is where we do find the artist's ID and the artist name. Indeed, again, if I open this up even further, then you'll find that each of these tables, there's not quite as much information as I would like. In fact, whatever IDs those are, to be a bit more prevalent. And indeed, that's because in the world of databases, and perhaps some of your own spreadsheets too, it's conventional, and I dare say best practice, to start to normalize your data, to normalize our data. We should avoid, let's say, having redundancies in our data, to normalize our data within tables and within across tables as well. That means then, again, if you consider our spreadsheet so our spreadsheet of users here, for example, the one that we're trying to get into the database, if I then had a column of, say, address, and I proposed that my address was 42 Wallaby Way, Sydney. Now, it turns out that there's a few other people in the world at that address, okay, let's say, Nemo amongst them, and the girl with the, with the braces, and so they might have that exact address as well. For those that don't know or don't remember, that's a reference to Sydney, yeah? I mean, Finding Nemo. 42 Wallaby Way, Sydney is where the fictional address where little Nemo ends up in. So, it turns out that if we have a lot of people maybe at that address actually doesn't lend itself very well to maybe printing nice on an envelope, because all I did was separate things with a comma, yeah, with this thing there, and actually not hit enter. In fact, because everything was all in a column, everything was all in here, it would actually be quite difficult then to search by, say, things like postcode. And for me, all the users from Sydney in, say, 0, 1, 2, 3, 4, 5. Well, we could sort of do it by searching freeform, and I could maybe, with my own eyes, kind of eyeball all the values there in the same column. But that's not best practice. It's definitely not clean. It's definitely not efficient, because you would have to look at them one by one and sort of ignore all the other words, ignore the other numbers and the like. Sydney, Australia, if I only were to care about the postcode, for example. So let me forge on my head there and say, is there a way for us to maybe, this database right now is seemingly, at first glance, more complicated than you might like. If we go back to the spreadsheet, what should I have done with the address in order to normalize my data? So what can I have done? Okay, that's a little bit... Well, okay, let's come back to it. If we think then about address, for example, well, I might would have started with, I could have quantized that value into, say, the street, and then the city. Could be one way around this, and then maybe the state, maybe the postcode. As Brian says, split it up. Not into one column, but split it into several columns. In fact, what I'll go ahead and do is I'll just separate this, and not just by having the address into the streets and then the city and the state and the postcode, but what if I delete the Sydney part, and then for each new column to the right, I'm able to be very precise with the type of data I have inside. So let's say, for example, I have the street. Whoops. No, let's say this will be the street, okay? So the street can still be 255 as now Sydney, so that's Australia, because I don't really know the upper bound for this. So I don't know how long a city can be. I just say 255. I say Sydney. In the state off to the right, and just like in Brazil, if I'm going to be smart in assuming that users are in Australia or in a country that does this idea of states, then I'll go ahead and just say that we'll use the character or car2 just for that 2-character code. So let's say Sydney SY, for example. Come on. And then for postcode, one more to the right, well, I'm too preemptively here saying trying to avoid the mistake I had earlier, which postcode start with a 0, because it could happen. So, if I do 0, 1, 2, 3, 4, then I'm rather just going to have, say, a character instead. So I'm going to say character. I'll just keep it simple, say 1, 2, 3, 4, 5. Where, again, I would have to specify that it's just an integer. I might actually close that mathematically to the first digit. But by storing it now, even though visually not really, but just as if it were 5 characters, and again, no hyphen or 4 others, can I make sure that if it were 0, 1, 2, 3, 4, 5, it stays exactly with a 0. But even 2, here we have a bit of an inefficiency, because imagine if I started to have more and more and more and more users within the same building from this particular application, perhaps, or this registration form. So you might have again and again and again the exact same values that I've just posted here, repeating if all my colleagues end up in the same building, like that. And so, as with programming in general, as soon as you start to see more and more redundancy, the same data appearing again and again and again, then that is definitely an opportunity for us to have better design. This is correct. Don't get me wrong. Colleagues and the fish and the people who live here might also live there if they add the names to the left and perhaps the distinct emails or distinct usernames. But we don't necessarily want to have the same exact text stored again and again and again. So what might you do? Even in the case of spreadsheets, how might we do this? Well, one way around this is actually not just having one spreadsheet, but actually have 2. On this sheet, I might actually just make, I might rename this to something like users. Okay, and you know what? Let me go ahead and actually, while I'm here, create myself another spreadsheet. And I'll just call this one cities, like so. And now my cities, if I go back to this one, might actually end up something like a city name. Oops, daisy. So it might have a city, it might have a state, it might have a postcode. But I could be smart and I can start to assign to each of those cities some form of identifier. I could start to give them an ID or a unique ID of sorts. And so here I might typically have a unique identifier, typically something like an integer, because that's a value with a high cardinal number. So let's go for an integer, where a city might be something like, again, like bar car, 255. State, if you're going for that 2-character system, might be car 2. And now postcode, meanwhile, if it's a 5 thing, I'll just say it might be a car 5. Yeah. But now, like, what if I can do is, let me presume that if my Sydney SY12245, if that's in this sheet, the one I had here, if you will, like this table, but if I want to grab this and actually, no, I'm going to grab this and then bring it to my cities table, post it in, and rather arbitrarily, I'm going to give this a unique identifier of, say, 1. Let's start at the top, let's say. And again, if I was to add more cities down below, like Brisbane or Perth, I don't know anything else, but then I would add 2 or 3 or 4 or some other unique identifier they're in. Because now that I have this table, now that I have this data, here's where you start to get that relational aspect, is where I can start to relate tables or spreadsheets together, if you will. So I can relate this sheet to this sheet as follows. Now, if back in this table, back in this spreadsheet, is I can go back and actually start to, I suppose, delete a lot of this redundancy here. So why don't I actually go ahead and say, I'm going to delete these 2 columns, gone. And I'm going to turn city, not into city, but let's turn city into, say, a city ID, hence like that. And so now it could be not this, but actually a proper integer, because remember we're using city ID, because the city in which all my colleagues live is exactly the same one as mine. So let's not do Sydney, but actually always pointing to the same one, which is good in that case. Now, there is still improvement to be made, an opportunity to be fair, because if all of us still are in the same building, perhaps, maybe that should be factored out as well. And I really want to get into the rabbit hole. I could get like another sheet or another table called, say, buildings, and I can factor that out too, like 42 Wallaby Way, give it a unique name, a unique ID, and then only store numbers within that building. So in short, the more redundancy, the more waste that you end up having in your data, then there are more opportunities there are to, say, normalize your data, to factor out those commonalities and create relationships between some pieces of data and others. Pointers, like Nick says, and the convention in computing is to do, well, quite simply just the numbers. Why? Because numbers, as it turns out, are just much more efficient for the computer to relate and point to some other point of data, just by relying maybe on, say, small integers like that. 4 bytes, it's not that much. In fact, inside of a computer or a CPU, CPUs have these so-called registers, tiny pieces of memory, which can be used on the most basic operations, addition and subtraction and comparisons for equality. And so with small integers like integers, can you very quickly start to reassemble? Can you then, with ease, start to relate and point some data to another one? So this is the general principle of maybe database design, is start to normalize your data by factoring things out, but reduce the amount of redundancy within. So that if we go back to our musical database, let's say, and perhaps we can infer maybe the author, if I close these tables up, so we can start to think in terms of database design here having been properly normalized. Why is it that the author doesn't appear here? I mean, maybe why the author of this data did that preemptively of trying to put things into different categories or normalize, say, having their albums, by album ID and title, which is, again, the number of that. The title is going to be the name of the album, and the artist ID, which is, again, a way for us to associate the albums table with the artist table. So they've used not the artist name, but an ID, an artist ID. So in this way, can an album have the same artist as another album without storing the artist's name twice? Moreover, as well, is if the artist happens to change their name, which can happen all the time, it's not uncommon in the musical world, so to change a name, you can then change a name in just one place and then not have to scour your tables for multiple copies. So again, good design. If you start to continue this logic through, you start to see more and more places, more and more tables, that we have this principle of naming this data and then assigning it an ID, something with a high cardinal value. And of course, if you want to relate some of this data to another data, you simply store the ID, okay? Not the actual values, just the ID. Of course, this becomes decreasingly useful as we go, because now some of my data is stored in this table, some of my data is stored in that table, and some of it's over here and over here and over here. And whilst, very clean and very refined to look at, sure, it doesn't seem useful to me anymore, to the data scientist in front of his or her computer that just wants to answer questions about the data, and yet it's all over the place, it's all over here. Whereas before, at least with spreadsheets, at least with Google Excel, I could just put up a window. It seems a lot cleaner to get to. But that's exactly where and how the power of SQL itself comes in. Because SQL doesn't prescribe how to query or type your data, it prescribes how to query it instead. So in this particular program, in say DB Browser, I can actually go over to this tab there, execute SQL, and again, I can start to execute those commands, run those commands, those actual commands, to select and the create and the update and the delete, the CRUD statements of the operations and others, to actually see the results. What SQL allows you to do is to express yourself programmatically by using a fairly small language, albeit now that allows you to create these temporary tables, just the results back, just the result set, so to speak, that you want. So you're able to spit out only the rows that you care about using this structured query language and query the bits that you're interested in. So, for instance, if I come back and if I wanted to say, I'm interested in so let's see if I can see all the albums in the database. So, in the world of databases and spreadsheets, I'll just double click and I would pursue in the Google spreadsheets. But in the world of SQL, I'm actually going to type in a command here. Like I'm going to go and actually type in the word select. I know it's really small. I wish I could zoom in, but I don't seem to be able to. Oh, I can. I just had to scroll the wheel. So, if in the world of SQL, the command select, and I want to say select star, wildcard, which is star for give me everything, from, select everything from, and I want to say the table, called album, and then the semicolon to finish up my thoughts. And I'm going to go ahead and double click on that little the play icon up above just to execute the command. And as we suddenly see on the bottom, lo and behold, all the albums apparently in this table that came back, all apparently, how big is that? All 347 albums in total, 347 rows are in particular from this database. And notice that all the titles are going to be in one column, so there's no column there. I'll zoom in, can't, but I've got the title column in, so the title in the center, I've got the album ID over here to the left, and as well the artist ID, of course, to the right. Now, again, if you're curious to know who is the artist behind For Those About to Rock, We Salute You, okay? I actually know this because I've been to the concert, but if I wanted to go and check it out, I could just make a mental note and say, well, that's the artist ID of 1. And you know what? With SQL, as it turns out, you can use predicates. You can qualify the data that you want. So you don't have to say, give me all, but you can say, give me this amount. How do I do this? Well, I can actually say, select everything from the artist, the other table that I've got, the one that we see here, this table, where, I'll do this on the same line for now, and then the predicate comes after where the artist ID, rather helpfully showing me, equals 1. So a semicolon again just to finish that thought. I'm going to hit play, and voila. So as it turns out, that is 1. I should want the, why is it not brought me back the results? Select everything from album, because I'm actually scrolling currently the album art, but it's not going to tell me the name of the artist. So how can I know the name of the artist if I'm not searching for the right table? Let me search for the artist table, where the artist ID is 1. That's it. So now knowing because the artist ID was set to 1, if I'm looking for that appropriate column, what? Is it because I reselected before? There you go. As it turns out, there you go. So it's AC/DC. I saw them in, ages ago, 2016 or so. It was when Brian Young was going deaf and I had to bring in the guy from Guns N' Roses, Axl Rose, and it was terrible. So anyway, this feels really manual. What I've done, it just it feels no better right now than the spreadsheet wherein a lot of the work seems to be on me right now. But SQL is much more expressive than just this. Not only can you go and select and update and delete data, but you're able to join data from one table to another table. And in fact, let me just go ahead and do this a bit more explicitly. So if I want to go ahead and select everything from that original albums table this time, but I'd first like to join it. I would like to join that table with the artist table. How? Well, if I want to join 2 tables together, so if I want to join this one and that one, kind of like this, so to speak, conceptually, I need to say on what fields, on what fields one is going to relate to the other one, how they're going to map. So on that then, I'm going to say on the album, so recall there's an artist ID, and I want that artist ID to be equal on both the album to the artist ID. So I'm going to say the artist ID is going to be equal to the artist table, artist ID. All right, so in other words, like imagine if you had this hand to be the albums, and this hand here to be the artists, and the tips of my fingers now each represent those individual artists ID and the albums ID. I essentially want SQL to use my fingers and make them touch so that you have the left of the albums and you have the right of the albums, and then each one of those rows now has both. Let me just finish my thought there, hit semicolon, hit play, and voila. So we now see, way more information, but all of it now together. We now see that album number 1, so For Those About to Rock, album number 1, with then an artist ID of 1, but clearly an artist ID of 1 but a name. Yeah. Well, what really happened was both of those tables kind of have been concatenated together, but joined together such as that the artist ID in both tables now line up together on the left and the right. And of course, at this point, I don't really care about the numbers. The numbers are just sort of surplus, and I definitely don't want the temporary duplication of the data. So I don't have to keep saying star, which is the so-called wildcard, which gives me everything. And so rather than giving back everything, I can actually just say, give me back just the title of the album and the names of the album instead. I just want those 2 columns instead. And I'll do that by specifying that with commas instead. So the name of the title and the name as well of the columns I actually need, rather than bringing back everything. If I now click play, I get much simpler results. I just get the titles and I just get the names of those artists too. Okay. So if we think about SQL as an implementation of this, like it is a language to be learned for sure, and there's a lot of things in this. How else can we represent ourselves? How else can we express SQL commands? Well, aside from CRUD, there are a couple of other keywords as well, just worth mentioning over here. That of things like where, and we've got join. You can also group values then by something. You can group them together by something and specify what they might have something as well. All of them that have something in common. Yeah. So let's go back and see. For instance, if I go back to my data here, I'll put that aside for a second, just to consider which artists have multiple albums. Okay. I mean, if we consider back the results of here, like the results that we had earlier, do we have AC/DC as well as for those About to Rock, We Salute You, Let There Be Rock, and so on. But moreover, we have the band Accept, but they have multiple albums as well. Audioslave as well. You can probably see others as well if you scroll down. But so what if I like to see those bands, the artists that have multiple albums, so those that have been publishing multiple times? How can we do that? Well, what if somehow I collapsed all the mentions of AC/DC into just one row, And then next to that row, I put the actual content, the actual count of all the dimensions. So what I could do is I refine the query as follows. What I can say is, yes, join these tables together, but I want to collapse them, if you will, like based on the groupings of some common value. So let's go ahead and group I want to group the table by the name column, so to speak, so that any artists that appear multiple times will effectively just be collapsed into one. And so rather than me having to select all the albums now, all the albums themselves this time, what I'm going to do is I'm going to select the album's name, and then I'm going to count thereof. So aside from the title and the name, I want to have the count of the names, thereby specifying, show me the name of the album, and show me the count of the name before we got grouped. So let me just get rid of the title for now, just to make that simpler. So this time, if I hit save and run, I'm able to execute in there. It's a little bit small here if I zoom in further. But indeed, if you can see, say, AC/DC. So AC/DC had the names of, for those about to rock and for those about to, the other one, but more than one. So did Amy Winehouse, so did Accept, so did Audio Slave and the others as well. So a few others as well had more than one. And again, if we kept scrolling, we'd find all the band names that had one or more albums for the count of each of those. But I like to remember how many rows got collapsed into just one. So if I want to filter out now perhaps those bands that had only just one hit album, only one hit album in this database, I can say, you know what, instead of just go ahead and group by the artist name, I want you to group by the album by the bands that have more than one album. So group them by artists that have more than one. So here I can go about and simply filter my results by literally saying that. I can say by having count name of more than one. So save that and hit play now. I'm going to get all the results back immediately, or close enough. But notice now I'm eliminating all those bands that had just the one album. And if I scroll down, I'm going to see bands that have 2 or 3 or even 11 Deep Purple that have more. And so with SQL, can you start to begin to express yourself? Certainly more arcanely than you could do with a click of a mouse or a spreadsheet, but much more powerfully now, much more selectively if you want to. But the key is to build up your queries by piecemeal. And you're like, already this looks kind of complicated just by first glance. But if you began just by selecting all the data and then refining, thereby working at this level and only getting, once we already know what we wanted, notice how quick we're able to bring those operations, how fast they've been. Indeed, at the bottom of here, I see 56 rows returned in 21 milliseconds. And even though it would probably take me longer to describe in English what it is I wanted, in fact, the computer can find it that quickly of all the information that there is. And that's because, well, we've done one thing right already, that this data is already organized with its proper types. But it has a few other key characteristics as well. Namely, when you are storing the data in SQL, in the database, you're asked to answer some questions. So for every table, you're effectively asked to say what, if any, is this table's primary key? So these are keywords in SQL that you can apply to some column that says, hey, database, draw on the pen. Whatever my primary key value is. So my primary key is a way of saying, of all the other ones, my orange one is the one that uniquely identifies every row, every record in my table. So in the context of our own user spreadsheet before, which we began, remember that's to say that the city was the primary key. Well, I might very well have used the city's name as unique, but perhaps even the postcode. But again, just to be more efficient, especially if you want to avoid ambiguities and the like, if you want to avoid duplication, it's just to use integers. So usually you'll find that almost always now, the primary key is one of a high cardinality value. A cardinality value is refers to the discreteness of this, the number of distinct values. So city or Sydney, streets, while being quite unique, and even then is a loaded word because to be unique, it is truly unique, but to be kind of spaced out as it can be. And I can't think of anything spaced out as a number, because blue, brown, green colors, you might have several that fall in that pot. But unique values like numbers, often integers, almost always are numeric values. They're the most optimized for that data. So it just guarantees that the database there will be no duplicates of that particular value. And good, pleasure. Thank you very much for joining. Good night all. I'll carry on. Just to forge on with the types of data I have. Thank you, I'll see you soon, okay? We're able to, so we can define one table in the column to be the primary key, but in another table, the so-called foreign key. In other words, so throughout this example, like in the actual SQL database, I had albums in one table, I had artists in another table, and so on. And in the artists table, if we go back actually just to show you, so the artist table, this table, that was known throughout as our primary key. But when you saw that artist ID as the albums table, within here, conceptually, contextually, that was the foreign key because it was referring to a key from another table. Now, beyond semantics, this is an actual and this is a valuable property to have because that makes sure that the table knows how to link between two columns efficiently. Again, if you have even fancier features available to you when you declare keys, you'll also tell the database, you know what, if I ever delete this artist, just go ahead and delete all the artist albums as well. And if you configure a database automatically to have a so-called cascade effect, whereby data is going to be updated and your data is consistent at the end of the day based on those relations, it will. Now, columns of data that you can specify that every value has got to be unique. It doesn't necessarily have to be a primary key, it might still be unique. Like what? Well, in our users table, for example, we would create on the fly an email address for, by human convention, an email or domain is unique. Assuming I don't share it with anyone else, but using an email address, multiple characters, multiple possible characters, it tends not to be the most efficient way to search our data. So even in my users table, I might have added for best practice a numeric column as well, probably called an ID as my primary key. But I might still specify when moving that data from my Google spreadsheet into a SQL database that, you know what, please make sure that this email column, so that I or some other programmer doesn't accidentally insert or duplicate data into the table, make it unique. And moreover, the database then is able to search through more efficiently because it knows how many, if any, there are of one value. So that's one and only one maximally. Lastly, as well, we have the word index. It's another feature where you can get so powerfully from a proper database is the ability for you to search and sort values more efficiently. But the database doesn't know a priori how to do that on the data that you care about. Like, it doesn't know what you want, because only if you tell the database what data you plan to search for and sort for frequently, it can help you in advance. And so if you're creating a database table, you tell the database server, say, look, go ahead, index this column, and what it will do is it'll make a database structure, like a tree structure, not unlike the so-called binary search from before, and that will pull up all the data in sort of an artist rendition thereof, thereby ensuring that it doesn't just take as many as this step to find some email address or something else because you have indexed that particular column. So it doesn't store that linearly from bottom to left. It will store this kind of in a two-dimensional tree structure of some sort, often known as a B tree. It just allows you to go and grab that data, and hopefully logarithmic time as well, and not linear time. And it turns out that there are still even more features that you can get from an actual database, like from SQLite. Well, you have the ability to specify when you are creating a table, like, actually, please go ahead and auto-increment this column. What does that mean? Well, I very manually just a moment ago remember I assigned Sydney the unique identifier of 1 and Brisbane of 2 and Perth of 3. But why should I, the programmer, even have to worry or care about what the unique values actually are of my inputs? I just need to know that the key exists. I don't need to care about what the value is. I just need to know that it exists and that it's unique. So what we can do is we can tell the database on its own, please go ahead and auto-increment. So any time that I add a new row into this table, increment that value automatically. So you can also specify to a database, please make sure that no values in my database are null, that is empty. So thereby making sure that a bug in your code or some missing user input doesn't accidentally put into the database a row that's only sparsely filled with data, okay, real data. But the database can help you find and sort those things out just like you can in languages too. Just another layer of defense put into before your data as well for SQL injection attacks. And then functions as well, I just had a look at. So again, SQL is technically a programming language. It might not necessarily have as high ceiling as something as Python, but as much functionality into it. But inside of SQL, there are a number of functions. And again, if I were to take the average, the revenue across all my purchase orders, or I could use the average function. So in my SQL query, I can select the data, I can pass it into one of these functions, and then get back an answer from that without having to, say, copy and paste that into a spreadsheet or let alone a calculator. I'm able to count the rows just like we did. I'm able to count the number of appearances of the number of albums, or the number of albums that a given artist had. So count was a function supported by SQL. I'm able to get max as well as mins as well, maximum and minimum. You can also get summations as well, so sum of value and a whole bunch of other features too as well into this language. And again, well, the tool that you might use might not be DB Server. Perhaps it's some other textual interface, maybe some other abstraction on top of this, maybe more graphical in nature. It ultimately is just executing on your behalf and just handing them off to the database for execution for you. It's rather nice. Now, with all those features that you get with the database, like, it sounds way too good to be true. You're able to scale. You're able to eliminate redundancy. You're able to still select all the data that you want. And also, yes, to your point, that's all written in SQL. Just like I was able to do the count function, I'm able to sum all the values together. So count by name. I'm able to let's sum something like the sum of something like numeric names. Let's try the count, and I can try nested joins as well. So what if I try that? What if I say try to count me the count function returns the count of how many times something has happened, and I can try to sum them together. How can I sum them together? It won't work in that context. It won't work. I'll try the average, maybe, as well. But to your question, it's just these are functions, inbuilt functions or passed-in functions that work within SQL. Average, it won't make a lot of sense there, but perhaps if we take a closer look at this, what about the average length of the title, for example, the track? That probably has something in terms of milliseconds. So the average millisecond integer here. So I'm able to find out across by album or by artist and so on and so forth. This is why it's kind of a textual language, but it's not as high order as maybe something like JavaScript or some functional programming language they're in. It is part of, these are just little inbuilt things that can help you get data out and in. But unfortunately, you have to start to think harder and harder about the design of your system, because databases are sometimes vulnerable to mistakes. Okay, well, consider, for example, something like Twitter. Okay, let's think about how many times something has been liked, or Instagram, or something like this. I think still to this day, Instagram's most liked photo is that of Messi after he won the World Cup. Yeah, so the most liked photo is still Messi today. How many times has that been liked? Or the egg. So somewhere in the, upwards of millions. So 75 million times. Instagram or Twitter or whatever platform you're using has to then keep track of the likes or the retweets. So if you go like Instagram, how many comments does a post has gotten? The most viral of media, those counters, those integers here, they might get incremented really quickly. And again, if it goes viral, if you and I both happen to view or like something at the same time or nearly at the same time, well, that interface from us, like into the system, might actually trigger some instruction or some server somewhere to tell Instagram or the database to increment some value because you like something, so +1 it. But how does a database go about by incrementing a value? Well, if the if we're using views, for example, okay, the value of views of the value is counts is somehow stored in a database, a column of type of integer, let's say, and let's say here, oh my goodness me, I can't get it to work. But if I was thinking about my views here, then I would say, select in order to go and get that value. So whatever value I'm going for, say, for instance, the 100 people before me has liked some post, and then that value comes back as 100. 100 people have liked this photo. And then I do a bit of maths in my code, maybe perhaps Python, and I increment 100 plus 1 to 101. And then I use the SQL update statement, as you can, to push that data back into the database to update it. But supposedly, what if you and I, anywhere in the world, both happen to post at the same time or nearly the same time, as can certainly happen if those posts are particularly viral? Unfortunately, the computer can do multiple things at once, or at least in such rapid succession that it appears to be the same time, but at a race of sorts. And that can happen. A race condition, if you will, as follows. If both my button and your button are pressed on our phones at the same time, or nearly the same time, it induces an execution of code on the Instagram servers that selects for the both of us the current count of views, how many people have viewed this photo, and suppose that both of the threads, so to speak, both of the SQL operations that select the data and come back with a value of 100, each of those blocks of code serving our requests go ahead and increment that value to 101, and then via SQL update pushes that value back up to the database. Unfortunately, because both you and I induce the evaluation of that maths at the same time, or at the same time, what that database might end up doing is not storing 102, but 101. In other words, if two people's input is triggering a race to the bottom, to update the data, the database had better keep track of who and what and when asked for that update. Otherwise, you might end up losing that data. Now, in the case of tweets, or the case of likes, it's probably not that problematic, but frankly, that's their business. But you can certainly imagine with banks or financial institutions too, where numbers matter even more, you certainly don't want to accidentally lose track of a couple of bounds. So how do you go about by solving this in all the SQL of the database? Well, it turns out that there are some fairly fundamental primitives and solutions you can use. Consider, for example, the primitive of a family refrigerator. Okay, so consider you or your significant other. You both happen to be coming home from the kitchen, from whatever, and you both want to look for something to drink at the end of the day. Okay, some milk or something. Let's not give them advertising, shall we? Otherwise, my feed will be crazy. So, say you come home before me, and you're and you're looking for something to drink, and there is no milk. Some milk. Like when you get home, and the other person's not yet home, you're the first person home. When you open the fridge and you see, oh damn, like there's no they seem pretty stocked up in this case, but there's no Fanta. Let's imagine I like Fanta. Okay, I'm out of Fanta. So what you do, you close the fridge door and you head downstairs and you go to the shop. Meanwhile, me, the other person, comes home and I'm wanting some Fanta. I open the fridge and, you know what, I'm out of Fanta as well. So I now head down the stairs, I go through the door, head out as well, perhaps in a different car, in a different route, and head to the store to go and get some Fanta. Fast forward some amount of time, both you and me come back from the store, and damn it, well, we now have twice as much as we'd like to. And it goes bad, or you both end up buying twice as much than you really only wanted one. So this is similar in spirits, because now you've got twice the amount of data that you actually wanted. Okay, it's not the right amount of data. What did that happen? Well, both of you, in the case of like say Instagram or the likes of photo, we both inspected the state of a value, we both looked at the value, the state of some value, we made a decision right on it as the other person was done acting with that information. Well, in the real world of Fanta or drinks, how can we avoid this conflict? How can we avoid that conflict, the race to restock the fridge? Well, some human intuition would probably tell us, simply grab a pen and a piece of paper and maybe write a note, so to speak. Maybe write something on the fridge that says, I've gone for milk, I've gone for Fanta. Okay, hopefully someone would not do the same thing. Or perhaps, rather more dramatically, what we can do is actually lock the fridge door, lock the refrigerator in some sense so that they can't even get into it and perhaps inspect the state. But ultimately, your act of checking the fridge and restocking it is what we'll call atomic in nature, atomicity in that sense. And databases hopefully do provide that atomicity, that property, the ability for you to be doing multiple things, many things, simultaneously or not at all, but not to be interrupted by someone else's work. And in the end, this atomicity, this acid principle in the database world, these are generally known as actual locks that you can put in to say to the database, don't let anyone else write code to this table or to this row whilst I'm using it, or be ready to release and unlock it after. Okay? And of course, tends to be quite a heavy-handed solution like we saw, so don't let anyone else touch the data. Better to do it at a much more fine-grained control so that you don't slow the whole system down, especially if it gets very viral. And so SQL databases tend to support what are known as transactions, whereby you can execute one more command again and again and again just to get back, but make sure that all of them go through at once before, say, your commands that your user input actually intended to do actually get executed. And honestly, even the most high-tech places, the Instagram, the Twitters of the world, this is a hard problem to get right. This is truly difficult because at some point, even waiting for my operations to complete before yours can go in is a bit of a challenge and a bottleneck for everyone else. And so in the case of the most viral posts, like the Messies of the world, what can systems do nowadays? Well, you would kind of just wait and write that data back to the database that's being updated eventually. And indeed, another property of databases is known as the idea of eventual consistency. A property that says, well, don't lose the data, but only eventually make sure it's reflected back on the server in the interest of time. Eventually get that value right, but do get it right. And so what Instagram and what Twitter and others do is, following that acid principle, is they'll often just cache or buffer that data, just waiting until things have quieted down a little bit, until the post is no longer viral, is no longer surfacing up, and most users have gone to sleep. Now, that alone might not be the best of solutions, but architecturally, it avoids having to get the highest reward, the most high-end or the most powerful of hardware servers. Of course, in other contexts, that might be the better solution, but in the world of finance, sometimes it's better just to, it comes down to the actual length of the cables, the direct connect distance, or the distance from some server to another hardware to actually make sure that the data gets so fast so you don't run into those sort of challenges. So databases can solve this to an extent. The developers, the designers can use those databases too, but they need to know how to do it and that they should also. Lastly, there's another challenge as well, unfortunately, all too common nowadays too, because folks just don't defend it against that too well with common mechanisms. It turns out that a bad actor somewhere on the internet, on your own network, can potentially, if you're not careful, trick the database into trying out things, executing commands that you didn't intend to do. So for instance here, say, in the context of bad Python, if you will, some code that looks a bit like this, it's written kind of pseudocode. Python that's just designed to allow a user to input the title of an album, which I wanted to search for, so looking for this particular album. And so for that, then I use the function input title, just to prompt the user for that title. So on the left side, I have a variable there. I've declared this called title, and then I've assigned that from right to left. So the user responds to that variable. Then for the sake of discussion, I'm just saying that there is a function called execute, and the purpose of execute is to take in that input and the input that I've designed above, and then represent a SQL command. But that SQL command looks a bit like this. So select star from the artist album where a title is something. Well, what is something? If the user's input has a variable called title, and I can use this plus operator in Python, not to add, but actually to concatenate two strings together, coding them singly and kind of completing that thought, let's say. The problem, though, is SQL shouldn't trust user's input, because whether their user input is coming from the keyboard, the Mac, or the PC, perhaps more compellingly from an app or a website, you probably shouldn't trust all your users. Because suppose then that one bad user perhaps typed in not the album's name for which they want to search, but, let's say, Let There Be Rock, but rather they typed in something like Let There Be Rock, delete. Thereby, apparently using SQL's apparent delete command in order to trick the database into executing not one, but two commands, a select and a delete. And indeed, this is what we refer to as being a SQL injection attack, the ability for an adversary, a bad actor out there, to somehow trick your database and your code by extension into trying out a command that you didn't want them to. How's that possible? Because some of these characters are dangerous, so to speak. A semicolon in SQL, a semicolon is used to separate one command from another command. It finishes your thought. And if you yourself didn't anticipate that some human or some bad actor might type in themselves a semicolon when they really shouldn't be typing in semicolon or SQL at all, then you might mistake that semicolon for the actual terminus between one command and another one. And so you just blindly pass into your server and let it execute as usual, but you might not execute that select, but the delete or anything else as well. And in this way, can a bad actor not only delete your data from your database, but maybe select more data than you intended to, or maybe update more, or insert more. It's really ultimately up to you to defend against these threats, whatever they may be. How? Well, it turns out that there are libraries, there are codes, there are things done by other users today that, frankly, via very easy to use functions, just make it easy to sanitize or maybe just to scrub, so to speak, user input. What these parameters do, these libraries or these functions typically do is, honestly, they just escape. They escape those dangerous characters. Something like a semicolon, perhaps like a single apostrophe that might, in SQL, have some special and dangerous potential meaning. They just escape them as having a backslash or a special character like a question mark in front of them, just so that if a human were to type in "Let there be rock," semicolon, delete, then that would actually be interpreted safely by a database as reading this like for an album called "Let There Be Rock," semicolon, delete, which of course the most likely is no such thing. So that query likely wouldn't bring back any results. But more importantly, it wouldn't be tricked. It wouldn't be SQL injected into running a command like this. Rather, it would just execute only the select query with a nonsense value, let's say. All right. I am running over time, but just if you're with me, consider what a database really is. Ultimately, it's just a piece of software. Ultimately, all of this is just running on a computer somewhere, be it on my own Mac or your PC, some server in the cloud. But if you have just one database, I seem to be presuming, we're just dealing with one at the moment, but you so have this single point of failure, if you will. Again, because just like we have in the world of cloud computing more generally, if you have something like data that you don't want to lose it, you don't want to suddenly all your web servers or your apps to just go offline because of your one server, your database server has gone out, then it's time to revisit architecturally the topology of systems more generally. Something that tells me it's not sufficient just to have one database. You probably want two databases. But if you have two databases, now how do you then decide where to put the data? Do you put it over here? Do you put it over there? Or in maybe cases, do you put them in both? And if you put them in both places, in both databases, then you're using twice as much space, twice as much cost, twice as much money, or sunny space. So to solve one simple problem, don't be a single point of failure, but that's going to cost you some time or some money or some space. Well, odds are, what you can do if you're architecting a system that now has not just web service, but a database, you're going to have to want, let's say, not just the one pictured here is a cylinder, as convention, but you're probably going to have a second one as well. But odds are, if you have two databases, odds are it's not sufficient just to store half of your data on one and half your data on the other, because, of course, we've not solved the single point of failure problem. Now we just have two single points of failure because half your data is on one and half is on the other one. So odds are then that you want to start to save backups as well, backups of your data. But again, you don't necessarily want to waste time restoring from backup, especially if you want to maintain your 5 nines of uptime, So odds are you want to have to actually store these databases in RDS as duplicates of one another. And whenever you write to one database, you should probably write it to the other one as well in parallel. So yes, admittedly, we've now spent twice as much space with twice as much, frankly, cost and money. But at some point, these sort of costs are just inevitable. There are other ways as well to scale here too. You could, of course, hit a ceiling in terms of vertical scaling when it comes to databases, because after all, if a database is just a program, it's software running on some server, and that server there's only a limited amount of RAM or disk space or CPU in that one server, eventually you're not going to be able to store as much data as quickly as you might want. So what can you do? Well, for instance, what you might do is actually end up sharding your data. To shard your data means not just have two, but actually maybe 4 servers that pull all your users whose name starts with, like, let's say A to M on maybe one half of your cluster of servers, so to speak, but everyone else from, say, M onwards to Z, or say the last names can go on the other one. So to shard a database means to split the data in some predictable way that you can then repeat again and again. But even there too, even if the only the A's through to M's are going to be to the left, you want to make sure that you still have backups as well as the replica as well. So as the arrow suggests, that these really should be intercommunicating between the two, not unlike load balancers we've seen in architectures. But another way you can scale your databases too, like you don't have to make the databases both be reading and writing. To read from the database or from a server means to take it from memory and to read it back into your memory. And to write means the opposite, to save it. Well, what you can actually do in the world of databases is also replicate your databases multiple times. And you might have connected to those your two primary databases, let's say your two primary databases, with multiple other databases, which are just copies in one direction and not both. And so what you might end up doing is having two primary databases, not only to read, but to write, rewrite databases, albeit, abbreviated RW. But then the other databases down to the right and left, which are just copies to the ones that they're connected to, they're just called read replicas, RRs, okay? They exist solely for the purpose of reading from again and again and again. Well, when might this make sense? Again, in some contexts like social media, like Instagram, Facebook, it's probably the case that there are more reads than there are writes. That is to say, you probably know more people who post more content than you, but you probably will have more that will look like reads still. So for your data, for your business, it follows that pattern whereby writes are maybe more common, but reads are way more common. You can do exactly this model of replicating data again and again. But honestly, a tree structure for efficiency, it doesn't have to replicate all one at a time. But then again, you can still write software, be it in Python or something else, that writes data only to one of the or two of those servers, but reads from any number of them as well with an in-memory database. But this too, again, is a bit of a rabbit hole, because at some point or another, you still have to think about the redundancy, not in just one location, but in all the locations, East Coast and West Coast, one country and another, because at some point, you might actually run into the limitations of time, okay? Because after all, it takes a non-zero amount of milliseconds for data to travel from one place to another, distance-wise. Consider, after all, how long it would take data to get from Sydney to somewhere in the UK, far longer than it would be for you to go down the road. So here too, we can revisit the problems that we saw in the world of cloud computing and service more generally. Then they're back to revisit the world of databases, but again, with databases, you care ever more about these things to go not down, or if they will, that you have spares or backups or replicas, because now we're storing our data in a centralized place. So we don't have to think necessarily about how they're scaling computationally, but how they're scaling in terms of our data inside of them as well. Okay, all right, so just to rewind and consider where we began, we started again by laying data out in a spreadsheet of sorts, be it in Excel or spreadsheet or the like. From there, we then started to think about how we might normalize our data, how we might store the data so that if we wanted an upgrade, so to speak, from a spreadsheet to the database, we knew exactly what types of data to specify. And in the world of SQL, so within SQLite or Oracle or MySQL or something else, they tend to be standard types that tend to be common across platforms, albeit with some variations, so that they can think hard about these types and ultimately help the database be more performant. Because if I know that I'm going to be searching and selecting on certain data, I can tell the database a priori, for instance, to make it unique or to make it at least index it. And then using SQL constructs like select and insert and update and delete, or CRUD, can I then manipulate the data in order to get it back more efficiently and perhaps, frankly, faster than the human would be able to do with the spreadsheets. But with the design of any database and any system as well, we start to open a can of worms and new problems as we start to explore more sophisticated challenges. But here too, we have many, if not all, the problems that we solve by simply just reducing the problems we have to first principles and consider, well, what's the principle to be solved? What can we do? How is the data represented? Where is it stored? And then think ultimately, what are the business constraints? What are the legal constraints? What are the financial constraints when we have about manipulating the data, and consider what tools are trade available to us? Okay, so that is then to the design, hopefully, more generally the design unto itself, and not just focusing on the correctness of implementing solutions to the problems, but getting the efficiency and the scalability as well thereof. Pleasure, Gareth. Thank you very much for sticking around. Raymond, Wilson, Wally, Willis, Coyote, Esperanza, Gareth, Raymond, Nick as well. Others too. Thank you very much for the session for the evening. It's Friday, so have a good one. Wonderful. Thank you very much, Raymond. That means a lot. It's good just to get familiar with the basics and let that be hopefully a step up. A pleasure. I'll see you very soon, folks. Go and enjoy your weekend. I'll see you all next week. Take care.